Okay, let's start out by looking at this pretty function here in red. Now, what we want to describe about this function is where it's increasing and where it's decreasing. So think of this function as a roller coaster, okay? And we always travel as x increases. So along this x-axis, as we go from left to right, x is getting bigger, right? So we look at this function in that same context. We're going to go from left to right as x increases. All right, so as x increases, you can see that on the roller coaster, we're going up. We are increasing. Our function value is getting bigger and bigger and bigger. That is the value along the y-axis. So along this interval of x, we're increasing. The function's increasing. And then right around here, when x is -1, the function starts heading downhill. That is, it's decreasing. And then it keeps decreasing till it gets to about here. Looks like x is around 3 right there. And now the function's increasing forever and ever, amen, to infinity. Okay, so what we're going to start doing is describing where along the x-axis, what interval of x the function is increasing on, and what interval of x the function's decreasing on. So it looks like the interval that it's increasing on is going to be from -infinity, because it starts from way down here, to -1. And then from -1 to 3, the function's decreasing. And then from 3 to infinity, the function's increasing again. So this function's pretty easy to see. It seems like it changes directions at x equals -1 and 3. But as you can probably imagine, not every function is that easy to read. So we need a way to algebraically say where a function stops increasing or starts decreasing, etc., where those intervals stop and start. And so we're going to use this idea of the slope of the tangent line, i.e. the derivative, to describe where those things occur. So I've got a tangent line here, and as I move this green dot, that's x increasing, right? You can see the function value is getting bigger and smaller and bigger again. And the tangent line is traveling along the function. And what I'd like you to notice is that the slope of the tangent line is positive here, right? It's going uphill, positive slope, right? So everywhere, remember the interval from -infinity to -1 has the function increasing, right? And look at the slope of the tangent line is positive on that whole interval. And then right here, we've got a horizontal tangent line. And then as x gets bigger than -1, look at now the slope's always downhill. In other words, the slope is negative on that interval where the function's decreasing. Here it's going to change direction again. So the slope of the tangent line here, I hope you remember, the slope of a horizontal line is 0. And then it starts being positive again. Okay, more and more and more positive. And it's going to continue being positive as that function goes up. So this function is increasing where the slope of the tangent line is positive. The slope is decreasing where the slope of the tangent line is negative. And where the slope of the tangent line is 0 are opportunities for the function to change direction from increasing to decreasing or from decreasing to increasing. Sometimes you can get a horizontal tangent line like this, and then it just continues to increase. So it's just an opportunity for the function to go from increasing to decreasing or from decreasing to increasing. We'll talk more about that later. So let's look at an example. We've got a function algebraically defined, f of x equals x cubed minus 12x plus 1. You could go and graph it if you wanted to, and then you'd really be able to visualize where the function's increasing and decreasing. But here we're going to use algebra to figure that out. Okay, so part A asks us to find all the values of x that correspond to horizontal tangent lines. So again, remember that's where the function can go from increasing to decreasing or decreasing to increasing. Those values occur where the first derivative is 0. Okay, so we're going to find the derivative like we've been doing in all these other sections, and we'll set that equal to 0 and find that x. Part B asks us to use those values from Part A to find the open intervals on which the function is increasing and the open intervals on which the function is decreasing. So we'll look at the notation for how we give those answers. And then finally, we're going to sketch the graph of the function. All right, so let's look at Part A. First, we find the derivative of the function, and it was 3x squared minus 12. Hopefully you found that. All right. So in order to figure out where that first derivative equals 0, in other words, the slope of the tangent line is equal to 0, we just set f prime equal to 0. So 3x squared minus 12 equals 0. Take a 3 out. Ooh, we get to factor. Difference of two squares, my favorite. All right, so think about where that, where this expression can equal 0, right? It's the product of these two binomials times 3. The only way that that can equal 0 is if that guy equals 0 or that guy equals 0, right? So that happens at x equals 2 and negative 2. All right, so those are two opportunities. Those x values are opportunities for the function to go from increasing to decreasing or the opposite. So those are our horizontal tangent lines. All right, so as we drag that green dot around the function, right, that's where the tangent line goes horizontal and it has an opportunity to change direction. All right, Part B says we can use a number line to help determine the intervals. All right, so now we're going to name the intervals where the function's increasing and decreasing. So we're going to make a number line, and on it we're going to mark 2 and negative 2. All right, and here it is. Here's the number line, and really all you need to label on the number line is negative 2 and 2. Those are the only opportunities for the function to change direction, okay? But once you break the number line into 3 intervals, right, by marking negative 2 and 2, now all you have to do is check each of those 3 intervals for whether the function is increasing or decreasing, okay? And you can choose any value. So in this case, it looks like they used negative 5 for interval A. It's any value that is to the left of negative 2 on the number line, or any value less than negative 2, okay? So negative 5 is what they used. I would have maybe used negative 3 because it's easier to plug in, but you can use anything that's easy for you. Now, you're going to plug that test value in to f prime, again, because you want to know whether the function is increasing or decreasing. And f prime, the derivative of the function, tells you the slope of the tangent line, okay? And if the slope of the tangent line is positive, that is, it's an uphill line, then the function's increasing there, which is what's happening here in interval A. They plugged in negative 5 to f prime, and that was, remember, 3x squared minus 12. So negative 5 plugged in here gives us 63. And you notice 63 is really irrelevant. All we want to know is whether it's positive or negative. 63 is positive, so a positive slope on the tangent line indicates that on that whole interval, the function is increasing, okay? So then it increases till x gets to negative 2, and then it flattens out, right? That's where you have a horizontal tangent line. And now it might start increasing again, or it could decrease, which is what it does because they chose the most popular test point, which is x equals 0. Between negative 2 and 2, you can pick any value. 0 is usually the easiest. This one was. Plugging in 0 gave us f prime of 0 is negative 12, which is negative. That means that on interval B, the function is decreasing. So in other words, from negative 2 to positive 2, the whole way, the function is decreasing. And then the same thing for interval C. They chose 3, plugged it in, they got a positive value, which means that all the values after x equals 2, all the values are positive. In other words, the original function is increasing there because the derivative is positive there. All right, we'll do more examples. All right, so, all right, they showed you what they did. That's great. Okay, and ideally, we do these kinds of exercises because we want to be able to visualize the graph of a function. And so if you know where it's increasing and decreasing, you can draw a pretty good sketch. Okay, so not only do we know where it's increasing and decreasing, but we can figure out, for instance, where the y-intercept is. In this case, they plugged in 0 and got a 1. All right, and so let's see. So here's their sketch. So they've got from negative infinity to negative 2, it's increasing. All right, then it horizontal tangent line, looks just like my fun picture, and then it's decreasing all the way down here. They did say where it crosses the y-axis. It's pretty easy to figure that out. If you just plug in a 0 for x, you can get a y value. And then after positive 2, it's increasing. Easy peasy. Okay, so it provides a pretty good sketch. Nowadays we have, graphing calculators and Desmos, but it is still, it helps your math understanding if you can look at a function and have a basic idea of what it looks like just from its algebraic definition. All right, let's take a look at another example. This example is important because it brings up another really integral aspect of what we're doing, finding maxima and minima. All right, the function is 1 over x, simple enough function. Again, we're going to do what we did in the last example. We'll find all the values of x where the derivative is equal to 0, right? Those will be our horizontal tangent lines. And then we'll determine where the function's increasing and decreasing, and we can sketch the graph again. All right, so in order to differentiate, it's easier if we rewrite f of x using negative exponents, so x to the negative 1, and we can just use the power rule. So f prime of x is just the opposite of x to the negative 2, which if you remember, negative exponents is really 1 over x squared. Now remember, we're trying to set f prime equal to 0 to figure out where the function f of x has horizontal tangent lines. But 1 over x squared, or opposite 1 over x squared, is never going to be negative, right? Or I'm sorry, it's never going to be equal to 0. Okay. So there are no horizontal tangent lines. Okay, there are no x values which will make the slope equal to 0 in the formula for f prime. However, we note there is no slope defined for x equals 0. Okay, so if we go back to that, remember x equals 0 is undefined for f prime. Okay, so that is another place where we can check where the function, the original function, might go from increasing to decreasing or decreasing to increasing, because that means there's a vertical asymptote there. Okay, so it turns out that we need to put on our slope analysis line, that little number line, remember with the pluses and the minuses over it, any x values, not only the ones where f prime is equal to 0, but also any x values for which f prime is not defined. So that's x equals 0, and that's the only point we have to check. So our number line is only going to be broken up into 2 intervals because we only have one value where the function can go from increasing to decreasing or vice versa. So interval A, they use -1, and interval B, they use +1. And it looks like for in both cases, we have a negative value. In other words, it's decreasing from negative infinity to 0, and it's also decreasing from 0 to infinity. But remember, it's neither increasing nor decreasing at x equals 0 because the function, the derivative is not defined for x equals 0. So let's see, what does that mean for the picture? All right, that we already talked about. Look at that fun graph. I don't know if just from the decreasing thing we could have sketched. Okay, so summing up what we just did in the last 2 examples, critical values are what we call those x values, okay, where f prime of x equals 0, which indicates horizontal tangent lines, or where f prime of x doesn't exist, like in that last example, indicating vertical tangent lines or sharp points, okay, or in our case on the last one we had a vertical asymptote. And remember, it's those critical values that we use to break up the number line into regions that we can then check for increasing intervals and decreasing intervals. All right, let's play with another example. So our function here is a little more, it's not that complicated. It's a polynomial, easy peasy, right? Don't let that fraction freak you out. So first we're going to find the critical values of f. All right, so we'll find the first derivative, and then we'll figure out where that derivative equals 0, or where that derivative is undefined, and those will be all critical values. Then we're going to use the first derivative test to find any local extrema. So I'll describe what that is as we go through, and then we can sketch the graph of f. That's really just for giggles. All right, so let's look. So part A, first we're going to find the derivative. Take a minute, try to find the derivative, pause the video, and then come back and see if you were right. Hopefully you are. All right, the first derivative, negative 1/3 times 3x squared. Look at that, plus 2x plus 3, and that 1 goes away. Not so bad. Those 3's can divide out, and then you really just have negative or opposite x squared plus 2x plus 3 in a pretty fuchsia color. All right, so we're going to set that derivative equal to 0 to find the critical values. So what that means is opposite x squared plus 2x plus 3 equals 0. Look at that. Remember, we solved quadratics for days in so many classes. That's what you get to do again. This one luckily factors, and again you can use the zero product property? Oh yeah, that's what it's called. To show that if x equals -1, then that first factor is 0, and the product then would be 0. Or if x equals 3, same thing. So x equals -1 and 3 makes that equation true. So there are two critical values. So you're also supposed to look and see where f prime of x is undefined. And it's a polynomial, so there really isn't a place for it. So we just have the critical values of -1 and +3. So again, you're going to draw out a number line, and on it you'll label -1 and 3. And those two values will split the number line into 3 regions, 3 intervals. All right, so what is the first derivative test? Okay, first we find the critical values. You already did it, okay? Now you're going to make the number line and figure out where the original function is increasing or decreasing. Remember, the original function is increasing where the derivative is positive and decreasing where the derivative is negative. And so just using test points in those intervals. So a number less than -1, they used -2. You could have used -100 if you wanted. A number between -1 and 3, usually we use 0 when we can, because that's usually pretty easy to plug in, and it was here. And then a number greater than 3. You could use 1,000,000 if you want. All right, and then they used 5. So in the first interval, no matter what you use, you're also going to get a negative number, okay? Because we have proven that since the only place where the tangent line goes horizontal is at -1 and 3, then there's no other place for that thing to change. So all negative from -infinity to 1, so the original function f is decreasing from -infinity to 1. All positive from -1 to 3, so that function is increasing, and then it's decreasing after 3 and off to infinity. All right, so that tells us, oh, and in fact you can see these lovely little arrows. I've never done it that way, but you totally could. Now you can see this picture of what must be happening in the function. If it's decreasing on interval A and then it turns around and starts increasing on interval B, there must be a low point here, right? It's decreasing, 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 stop, increasing, increasing, increasing. So we call that a local minimum, okay? And same thing with here. We go up, 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 and then we start going down, 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 down. There must be a local maximum at 3. All right. So for both of the critical values, there is a sign change from one side of the value to the other. Therefore, local extrema, that just means a minimum or a maximum. Extrema is, well, it doesn't matter, okay, occur at both -1 and 3. So you want to know what the y values are, like how high is that local maximum and how low is that local minimum. And you just plug in the x values into the original function. Remember, the original function tells you the height of the function. So f of -1 gives you -2/3. Okay, and remember, at -1, back here, we noticed that that was a minimum. Okay, so -2/3 is a local minimum. All right, and then at x equals 3, remember, we decided that was a local maximum. So plugging 3 into the original function, its height is 10. So 310 is a local maximum. Isn't that fun? All right, so we can sketch the curve. f is decreasing on negative infinity to negative 1. Notice that is interval notation. In case you've forgotten, you'll be using it a lot in this homework. Okay, f is increasing on the interval from x equals negative 1 to x equals 3. All right, and I probably shouldn't have said that. It's not from x equals negative 1, but just past negative 1, and just right before we get to 3. That's why we use these rounded parentheses. It's called an open interval. You don't have to remember which one to use, because on these intervals, we're always going to use the rounded parentheses, no square brackets. Okay, f is decreasing from 3 to positive infinity. So that's the notation you'll be using in your homework. And then a local minimum occurs at the point negative 1, negative 2/3. And again, now this is an xy point on your function. And a local maximum occurs at the point 3, 10, where x is 3 and y is 10. And now they'll sketch it, and you can see there's that local minimum. So it was decreasing, 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 horizontal tangent line where f prime equals 0, and it occurs here at negative 1, and the function value, or the height of the function, is negative 2/3. Increasing, increasing, increasing till we get to x equals 3, and the function value, or the height of the function at x equals 3 is f of 3, or 10, and then it decreases after that. Isn't that fun? Doesn't it make you feel powerful? We know so much about functions now. All right, let's do another example. All right, now we get to use some of those higher level differentiation tools that we've been learning in this chapter. All right, so we're going to do the exact same thing. So we'll go through it pretty quickly. If I'm going too fast, you have all the power. You can slow down the video, pause it, go back, try to figure things out before we go over it together. So try to do A, B, and C yourself now, and then unpause the video again. All right, spoilers, I'm going to start giving you the answers now. All right, first we find the derivative of f, and we get, oh, look at that, 3 times the quantity x minus 2 squared. And again, remember, it's times the derivative of the inside, but the derivative of the inside is just 1. That's so fun. That's a nice, easy one, isn't it? All right, so we set it equal to 0 to find the critical values. And the only place where this is going to be equal to 0 is where that binomial x minus 2 equals 0, right? And the only place where that happens is at x equals 2. Easy breezy. Now remember, we also need to consider all the places where f prime of x doesn't exist. And we don't have any of those because there's no denominator for it to be 0, so easy breezy. Our number line just gets split into 2 intervals because we only have 1 critical value. And we check any test point less than 2 and any test point greater than 2. They used 1 and 3. Nice. And in both cases, we got positive values, which is to say that the function's increasing from negative infinity to 2, and it's also increasing from 2 to positive infinity. So what could that possibly mean? Why would the slope of the tangent line, why would the tangent line go to horizontal from increasing and then go to increasing again? Well, luckily, this example also has a sketch of the graph so you can see. Oh, another really important point. Since there's no change from increasing to decreasing or decreasing to increasing, there's no minimum or maximum, no local minimum or maximum. So there's no little bumps of hills or little valleys. Okay, what could it possibly look like? Well, there it is. It's just your regular cubic. All right. So you can see how the tangent line would have a positive slope here, and right here it flattens out, right at this point of inflection. Just slows all the way down to 0 and then picks up again and gets steeper and steeper as you go. Pretty cool. Again, the more we know about functions, the clearer it all becomes. All right, last example. We're going to find the critical values for this function. Now we've got a denominator, so things can get a little more interesting. All right, so take a minute, do all the steps to find the critical values here. Okay, so pause the video, and now you're back. Okay, good. All right, so first we're going to write it using exponents because it's just so much easier than using the quotient rule. Although if you used the quotient rule, that hopefully you will find the exact same value. If not, you messed up a little bit. All right, so dy dx is, again, they just use the power rule. So -1 times the quantity x minus 2 to the -2 power. Again, multiplied by the derivative of the inside, but again, that's just 1 because that x term. All right, so that's our derivative. So to find the critical values, we want to set that equal to 0. But now if you write it in terms of positive exponents, it's easy to see that this fraction will never equal 0, okay? Because the numerator will never equal 0. So y prime will never be 0, but the other place that we find critical values are where the derivative is undefined, okay? And that happens where x equals 2, because that would cause our denominator to be 0. All right, so the original function, though, if you remember, y equals 1 over x minus 2 is also not defined at x equals 2. So that means x equals 2 is not even allowed in the function, so it can't be a critical value for the function. But the function can still go from increasing to decreasing, okay? So even though we don't call it a critical value, that's a place where you can check to see if the function goes from increasing to decreasing, because you've got an asymptote there. All right, that's it. Sorry it's so long, but it covered 3, 4a and b, and that should be enough for you to do your homework. There are some doozies in the homework as far as the application problems, but I mean, application problems, word problems that are real, based on real stuff, generally have some crazy numbers. So just be really careful, go slow, be meticulous with your details, and you shouldn't have any problems. Hopefully you won't have to do one of those big ones over again like I did. All right, I'm going to go do 3, 5 now. Have fun doing your homework.